Welcome everyone to today's presentation. The topic of today will be about how data preparation, pre-processing, feature engineering, and machine learning models can help us predict things in a dataset. Today's dataset is for the ABC Bank. A bit of context about the ABC Bank is it's a system that's currently manually approving or denying credit card applications, and they are moving towards an automated system. And so they provided us with raw data, and we need to interpret this data to build an accurate model that can accurately predict whether the credit card application should be approved or rejected. So this clearly shows that this is a binary classification problem, as we can either approve the credit card application, which represents the value 1, or reject it for a value of 0. So the raw data was given, and so we need to explore the data to see what pre-processing is required to be done. So first of all, we will determine if there are any missing values, duplicates, or any inconsistencies in general. And so we used to describe the data, and we found that, first of all, we have mixed numerical and categorical data, as can be seen from the screenshot. So we have some values, some numerical values, which are like, for example, the number of children, number of family members, but we also have some categorical values such as income type and education type and many more. So it's important for us to understand our data types early on so we can understand what pre-processing and what modeling techniques can be applied in this case. And so we move on to the further data exploration, where we determined if we have any skewed numerical features, and we found that there are some highly skewed features, as can be seen from the screenshot. Typically, skewness should range around 0, so any value between negative 0.5 to 0.5 is accepted. So as we can see here, we have some very high values, and that means our data is very skewed, which, for example, in the case of the number of children, is to be expected, as most people have around 0, 1, or 2 children, but people who have more children are more of an outliers and are rare, so they skew the data set, which is a bad thing, because then the model cannot accurately predict what to do when the family has several children, and so it tends to overweight the rare extreme values, and we tend to be ignoring them. And so we have to ensure data quality at this stage to prevent errors from propagating throughout the modeling. And here we can find that we described the data, and we were able to determine using this data quality issue, which shows that for us automatically what any features and how we can make them better and to make our model more accurate. And here, for example, any potential anomalies. So for example, if there are too many outliers, how to fix. For example, it told us which categorical variables can be encoded to make it easier for us. So this step ensures pre-processing decisions are evidence-based rather than arbitrary. So in this case, it confirms that most are usable, but there are some features that need transformation or some pre-processing or encoding as well before modeling. So here we did our first pre-processing transformation steps. First of all, we dropped the ID column because it is a unique identifier because it determines each customer with no predictive value and could introduce noise into our model. So it was dropped. And then we clearly defined the target variable, which in this case is the approval or the rejection of the credit card application. So that's our target model, and that's how we proceed. And then categorical variables were label encoded, so the model could interpret them numerically and accurately rather than keep them as categorical variables. And then we also corrected the skew, which can be seen in the future slides, that we corrected the skew that would affect the accuracy of our model. And then here we have, again, after our pre-processing and transformation, we have the data set with the data quality issue column, and it shows us that now almost all of our features are usable. The ones with outliers are to be expected, which is the number of children, etc. These are expected outliers, so we need to proceed. And then issues such as skewness and inconsistent representations have been addressed, and now we have more stable features that we can use to model. So for example, for the skewness, as mentioned before, usually we prefer a lower value closer to 0. And after the correction of the skewness, most of our variables are closer now to the 0, so that it's better, so less skew. This improves our model stability and allows patterns to be learned more evenly across the dataset, as can be seen when we compare these graphs to the previous graph. So we have normalized the number of children, and now we can see clearly where we have the peaks and where we have approvals and rejections, and it's not affected by any outliers, which in this case we may have some due to the different amount of number of children. And so next we wanted to determine how we can simplify our model or if there's a need to. So we use this correlation heat map to visualize the relationship between the numerical features, and strong correlations, which are the darker colors, indicate that there's some redundancy, which can make our model more complex without adding any actual additional information. So this analysis helps guide dimensionality reduction and prevents multicollinearity from negatively affecting our model performance. So then we want to perform some form of principal component analysis to reduce the model complexity and while retaining most of the variance to the best of our ability. Now, this does improve efficiency, but our concern is then the bias variance trade-off, because then we decrease the number of components, which could then lead to a higher bias but a lower variance. And then here we wanted to split our dataset into target and predictors. So we have the target, which is, as mentioned before, the credit card status of the credit card application. And then we have the predictors in our case, which we're trying to see which factors affect the target the most. So then we do after we did the PCA, we considered components of 5, and then we did the PCA cumulative graph to see how the cumulative explained variance behaves under how many different number of components. So we can see that as the number of components increase, yes, the graph behaves better, but not significantly enough for us to resort to using the full amount of components. So we can accept to use less components. And as mentioned before, that would lead to some bias variance trade-off, because of less components means our model is less complex, but still that could affect the quality of our model and how accurate it is. And next, we verified the feature importance. So we measured how much each variable contributes to model predictions. It's typically calculated based on a feature's impact on reducing prediction error, particularly in like tree-based models or other models. High importance features, that is, for example, here, age, total income, account length, align with financial intuition, which is as predicted that, for example, if the older someone's get, the most likely the credit card application will be approved, their account, their high income. So it depends on certain factors that with intuition makes sense. So then we wanted to see, after encoding, we wanted to see the encoding strategy comparison. So we used binary coding as well as, which is a dummy encoding, and label encoding, which we've already applied. So initially we split our data into an 80-20 split to train the model on known outcomes and validate on the test data. Then we ran the delta test, which is to verify the difference between the binary encoding and label encoding to see which model was better. And then we wanted to compare the logistic regression accuracy with the random forest accuracy. And then we also wanted to track their performance by using certain important factors of the model itself, which are initially explained, which is the precision, recall, and then accuracy. So we can see that the models behaved with the logistic regression accuracy and the random forest accuracy were around 85% for both, which would be misleading and assume that the models performed well. However, if we look at the recall and the precision, we notice that there's 0 for all cases, which signifies that the models were unable to predict the positives. So the precision signifies false positives. Since the precision is 0, that means it wasn't able to predict any false positives because there was no positives at all. Similarly, for the recall, there were 0 false negatives. So that means there was no value of 1. So it means that the model, since they have a majority of the values are zeros or rejections, the model just chose to use all values to be 0 to accurately predict 85% of the time. But that introduces a lot of error in terms of false positives and false negatives. And that we can see that across the board in all the models, except, for example, when we look at the random forest accuracy with the label encoding, it's performed better in terms of precision. However, we still have a problem in terms of recall. Then we wanted to see the impact of k-means clustering, and in this case, we used 2 clusters, and we encounter some of the same problem as before, which is that the accuracy is high, which should be good, but the precision and recall are low. So then we use the automated model selection with H2O AutoML, which evaluates multiple advanced models automatically by itself. And based on, you can use certain factors, and we found that, as mentioned before, the accuracy, precision, and recall should be high for a good model. We found that, for example, the XGBoost Grid 1, which is line 11, performed the best in terms of accuracy, precision, and recall, but that could be contributed to several other factors. And so some models can be different, and so different models perform, and they obviously outperform manually selected approaches, the ones we've done previously, and they perform better overall. And so we wanted to compare overall the different methods used and which ones were best. So for example, the baseline, which is the logistic regression, as mentioned, 85% accuracy. However, this accuracy could be a trap and predicts only the majority and misses all the class 1 cases. And then we have the standard ensemble, which is the random forest in this case, performed similarly to the baseline, which is the logistic regression. Then we have the k-means, which had a decreased accuracy, and still didn't manage to fix the recall issue. And then when we were able to use the AutoML, we found that the top performer was the XGBoost Grid 1, as mentioned before, and it had the best balance in that it minimized the false positives and false negatives and accurately predicted most cases. And then we have an overpredictor example, for example, which is the XRT1, which had 0 false negatives, but creates an overwhelming amount of false positives, which means the model was not able to accurately predict the positives or the negatives. And so overall, our models have some strengths, obviously, but have limitations and implications in the real world. So the strengths of our models is that the structured pre-processing improved the model stability, of course, which is that if we left the model as it was, we wouldn't have had accurate models like we did after we pre-processed and transformed the data. And that the feature engineering can enhance predictive power. And overall, multiple models allowed for performance benchmarking, so we could compare different models. One model wouldn't have been enough. We couldn't have been it wouldn't have been sufficient to predict on one model and rely on it. So we use multiple to compare them and see which performed the best. For the limitations, the PCA, the principal component analysis, reduces feature interpretability. So we can't as easily predict which model affects which, because then it reduces the multicollinearity. So some of them are different. So we can't accurately use one predictor simply to predict whether the target will be a yes or no. And then the limitations as well is the encoding techniques introduce assumptions. So for example, if I use the label encoding for a certain categorical variable, how would anyone else who is reading this model know that 0, 1, 2, 3, 4, what do they signify? And then the dataset imbalance sometimes may affect generalization, so we can't really generalize based on some imbalances here and there. And what are the implications for this in terms of the large scale? They support automated credit card approval decisions. This is a good system overall. It could use some tweaking, but overall it did good. And highlights the importance of explainability in banking. We should be able to explain to our customers why we're approving or rejecting a system, so we should be able to understand it fully and why the data is the way it is. It enforces the need between accuracy and transparency and certain factors, because we can't simply say our model is accurate and accept that, because we have other factors such as precision and recall. So we must consider all factors in our system and not strike some sort of balance, because obviously no model performs perfectly and we shan't expect it to. Overall, data preparation is the foundation of a reliable machine learning model and outcomes. So we should be understanding of our data, explore it, and pre-process it in a way that ensures that our model will perform the best it could. Feature engineering overall is a very good way to improve the performance of our model, and advanced models often benefit most from well-prepared data. So the models we use, which are the k-means, the random forest, and even the like the H2O AutoML, you needed well-prepared data, which we were able to do with the pre-processing and the transformations. And overall, machine learning can support fair, efficient, and scalable credit decisions when the data we have presented to it has been well prepared and well thought out. Thank you.